All right, on with more recording. So let me just kind of go back to the first one, and this is the first time I have done this type of demonstration, but I think it's going to be helpful. So let me show you, the code equivalency in an actual C program. Okay, and I think this is going to be pretty helpful. So let's get out of here, and I'll just call this if C. Okay, if.c. All right, so what we'll do is we are going to write a subroutine to test that method. Two subroutines to be exact. Okay, so we'll have one subroutine void if1, and this is using a single condition C. And this time I'm not using the usual uint 64 underscore t because the width of the integer is of no concern here. So we'll say if C, a block of code for the then portion, and then another block of code for the else portion. And in this one, we can either print f, okay, to output something, or we can do something else. So we'll just go ahead and use printf in this program. So pound include stdio.h. There we go. And over here, we say printf. %d, which is an integer, is true. Okay, there we go. And over here, we'll say it is false. So not very exciting. Okay, this program doesn't do a whole lot. And then we'll write a second subroutine, which is if2. Same kind of prototype. It takes one single integer as its parameter. And this time we have the new format, which is saying if not C, go to label L1. And if we're not going to label L1, then we perform block 1, which is basically just printf. Instead of doing this, we can do copy and paste. So we copy this, paste it over here, and then we have an unconditional go to label L2, which is a continuation label. And then we go back to here, label L1 is defined over here. And then we have the second block of code, which is inserted here. And then we have L2 defined over here. All right, so let me just double check, make sure that this is consistent with what we are talking about. Okay, so it looks exactly the same, except the block 1 and block 2 are actual printf statements, but you can kind of imagine that they can be an entire chunk of code, multiple lines. It doesn't really matter in that case. All right, so now we have our main, and depending on how we want to test this program, I think we should test it with both true and false. So I'm gonna do this in a slightly more interesting way. So what I'll do is I am going to have two local arrays, okay? Because I want to test this code exhaustively, okay? So I could have done this by hand, but I want to show you a kind of more systematic way to do it. So we'll go ahead and first we'll look at all the values that we want to pass as an argument to parameter C. So we'll just go ahead and say int okay. There are two cases because it's either false or true, okay? So we can do a const int num C cases, okay? And that's going to be just 2. And then we have C cases as an array, and it just has 0 and 1. Anything that's other than 0 is fine. Okay, so basically it's just these two. And obviously this is the wrong syntax. Okay, I'm borrowing syntax again from JavaScript. No, in C, it has to be curly braces if we are initializing an array to begin with. And we also have to indicate that this is an array, and all that stuff. And then we have another constant over here, which is number of functions, which is also 2 because we have if1 and if2. And now we have an array of pointers to functions. Okay, this is going to be fun because some of you may not have exposure to how to declare an array an array of pointers to functions. So the way we do it as far as declaring the type is we say void, because these are all void functions, and here is where we indicate we're dealing with pointers to functions. Instead of the name of the function, which normally goes where the cursor is, I use parentheses, and inside the parentheses we do a star, which is pointer to, and then we name our array. Okay, so we say funcs or functions, and then we use the square bracket over here to indicate that we're dealing with an array of pointers to functions that return a void, but we also have to indicate what type of argument we are expecting, or what type of parameter we're expecting. So this is how we declare an array of this is the array part. This is how we declare an array of pointers to functions. So the function part has to do with this part over here, where we we can have an empty list of parameters. That's fine too, but we will have a pair of parentheses in this place. So now that is now defined to be ampersand if1 and ampersand if2. The ampersand, I think, is optional, because if you just say if1 and if2, because C is not like JavaScript or other programming languages, you can't really define a function somewhere else. Okay, so whenever you refer to a function and you're not calling the function, you're referring to the address of the function. So I believe the ampersand is optional. Anyway, so now we got this done, and then we'll have two indexes. Okay, so we'll have int I case, okay, or index of cases. So index of cases, and then we have index of functions. Okay, and both of these are just integers. So now we have for I cases equals to 0, and I cases, whoops, is less than number of C cases plus I cases. So basically we are saying for each C case, the index I is controlling that. And then within here we have another for loop, which is going to go through all the functions. So we now have I funcs equals to 0, I funcs is less than number of functions plus index to functions. So at this point in the innermost part of these two loops, we have now two indexes, and now we can specify what we are passing to test each one. So we probably want to indicate which test case we're dealing with. So printf would be helpful. So now we say C equals to %d, which is a placeholder for an integer in printf format, and then we'll say function is %d also. So this is going to give us not the name of the function. There's no way that I can know of to extract the name of a function in C from a pointer. But it would at least give us an idea of which test case we're dealing with, and then we just perform the call. So when we want to perform the call, we have to refer to the function first, right? So now we have to I think the parentheses are optional, but I'm going to put it in. So now we say funcs, which is the name of the array of pointers to functions, and then we supply an index to it because it is an array. So that would be I funcs, okay, index to functions, and then the dereference, okay, pointer dereferencing is also optional because C basically understands that when we refer to a pointer to a function in the context of calling, it is always going to dereference it, because otherwise a pointer to a function doesn't have a whole lot of use in this context. So now we can supply the arguments, or supply the argument. There's only one, which is C cases bracket I cases. So now both the function that we are calling is controlled by ifuncs, and then the value that we are passing as its argument is controlled by I cases, like so. And I think this program is done. Okay, so we'll see whether this even compiles, because it has been a while before it has been a while since I used pointers to functions in C. Okay, so we say gcc -g just in case I need to debug it, -o to specify the output, executable output of this program, which is if itself. Let's call this a.out, okay, because if is a bash command, so I don't want to confuse bash with an external command. There's a way to make sure that that is not the case, but a.out is a typical executable name in Unix/Linux type of environment. And then we just apply the name of the C code. And it doesn't like it because I probably forgot a semicolon on line 21. Okay, so let's go to line 21 and fix it. No, I did not forget that. So why is it complaining at label L2? Okay. It says label at end of compound statement. Okay. And the only compound statement that we have is the conditional statement. And this is the then statement of the only conditional statement. So it should not have confused with L2 over here. And I cannot get rid of L2. All right, so let's go ahead and put in a totally useless empty block statement here and see if the compiler still complains. Okay, well, what can you say? It is not an error to define a label at the end of, and I think in this case the compound statement is referring to the entire body of if2 as a function, which is kind of weird because it's it's actually a natural place to put a label, because if somebody wants to jump, use a goto, going to the end of a subroutine, seems to be a pretty normal thing to do, when the subroutine itself is encountering problems. So anyway, so we're going to run the program, which is a.out. So we run a.out, and we can see that the behavior of the program is kind of okay. So I did something wrong here. The behavior of the code is correct. It's just that, oh, I know what happens. I forgot one thing, which is not atypical of me. I specify printf. I specify there's a placeholder %d with the first one over here, and then there's another placeholder %d over here, but I never really supplied what goes into the placeholder. So I'm defining placeholders without actually telling printf what values are supposed to be printed at those particular placeholders. If I remember correctly, the C compiler used to complain about this. Maybe I just didn't turn on warn on. Let me try that again here. Okay, because I wanted this time, when I compile, I want to use w warn all. Okay, and okay, so this time it complains and go like, hey, where's your integer? You said that there will be an integer here, but you never really let me know where the integer is. So warn all is a wonderful option to specify when you compile your C program. All right, so now I feel better. Okay, so let's go ahead and fix it. I cases and I funcs. There we go. And recompile the code and then rerun the code. There we go. Okay, okay, this is great because basically we're looking at exactly the same behavior, no matter which function we're using and no matter which condition we are talking about. For the same condition, the two pieces of code behave identically, and that's basically the best we can hope for. All right, so I think this is going to be helpful because it illustrates that as we use the flattening approach on a C program, it doesn't change the behavior of the C code. It just makes it look messier. So if I go back to the code over here, this is the original, and this is the one after the transition. It just looks messy. Okay, it uses goto, which your other professors will basically totally frown on, but in the context of what we are doing, this is actually a good idea, okay? Because this makes the program one step closer to be able to be specified in assembly language. And when I say assembly language, I'm not just talking about TTP ASM, I'm talking about any assembly language. Because in assembly language, there's no such thing as a block, okay? The curly braces concept does not exist. So as we break down a C program or flatten a C program to get rid of these curly braces, that gets us closer to a format that is easier to implement in assembly language. Now, the second thing I also want to mention is the names of the labels, L1, L1, L2, L2 over here. Those are flexible, okay? I'm just using L1, L2 as placeholders. Which also means, when you are actually doing this type of code, you can use any labels and make sure that the labels are not reused or redefined, because that would not be a good thing. So if block 1 is its own conditional statement, you probably don't want to use L1 and L2 if you have already used L1 and L2 in the outer conditional statement. So block 1, if it is an inner conditional statement, you have to think of a name to use for those two labels, because you cannot reuse the same label names. Later in this module, there's a discussion of how you can name the labels in a very, very systematic way, so that there's no way, if you follow that way, there's no you cannot be reusing the same label names. But it does make it a little bit harder to track, a little bit harder for us to read, but it's a very, very systematic way to name the labels. So there's that. And for the same, using the same approach, you can now use the same approach on section 3.2 and basically convert a regular while loop, which looks like this, into a flattened while loop. Now this one looks kind of funkier compared to before, because the word while is completely gone. Okay, whereas before the word if is still around, it's just used in a slightly different way, but this time the word while is completely gone. Which is fine, because conditional branches is what we want to end up with, and this is a conditional branch. Okay, so let's kind of check out the logic of this translation. In the original code, it says while C block 1, which basically means we first check whether C is true or not. If C is true, we continue to block 1, and then we go back to recheck C. If C is false, then we get out of the entire while loop. That is the meaning of a while loop in C and C++. In the translated code, we first define the label L1 so that we have a place to go back to. And then the very first thing we do is to check whether not C is true or not. In other words, we're checking whether C is false or not. If C is false, then we go to label L2, which is a continuation label. It continues on with whatever code, if there's any, after the original while loop. What if C is true? Well, if C is true, then not C is going to be false, and therefore we are not going to label L2. So the program will then continue on to block 1, which is the body of the loop as in the original code. At the end of the original code, there's no goto, because the while keyword in C and C++ implicitly says after you perform the body of the loop, you have to go back and check the condition again. But since we got rid of the word while, okay, now we have to use an explicit go to L1 in order to go all the way back to the beginning to check the condition again. So in terms of behavior, these two pieces of code are identical. So this time I am not going to give you a demonstration, but you can go ahead and write one piece of code using a typical while loop, and then translate it into this kind of code for your for the second block, and then you can test it to see if they behave in exactly the same way. Now, do you want to use the approach that I used here, using a let me go back to the C code here. So defining while one and while two, and give it a different, I guess limit or whatever. Okay, it's fine. Now the question is, do you want to make an array of test cases and then make an array of functions? That's entirely up to you. Okay, so I'm pretty sure you know how to basically test what is in the notes here, but without using all the kind of slightly more advanced concepts of using an array of pointers to functions. But it's a good idea to test it. Okay, you can make a very small loop. All it does is to have an integer to go from 0 to 2 and then print it out inside the body of the loop, and do it one way using the original while loop, and then do it the other way using the flattened while loop, and just make sure that it works. Okay, so here's another idea. Okay, so I got a lot of ideas, right? So here's the other idea. So let's go ahead and write some code to do the while thing. Okay, so we have let's say while.c, and in here we have void while1, and this time it is just an empty, it has no parameters. Okay, so instead of block 1 and block 2 being defined and copy and paste everything, this is what I'll do. Okay, I'm going to use pound define. Okay, this may not be something that you have learned in C and C++, but this is what we call a macro definition, and I'll explain what a macro is and how to use it as we go through this program. So we'll pound define init. Okay, so typically the name of a macro is all uppercase in C and C++. So the init is really just to initialize a variable to, let's say, 0. Okay, so we say x equals to 0. And you can even do something like this. You can say int x equals to 0. Even that is actually okay as a macro definition, because basically every time the C preprocessor sees the word init all uppercase, it replaces it with whatever the definition of the macro is, which is basically everything after the name of the macro init. The rest of the line, including the semicolon, is a part of the definition of uppercase init. And then we can now define block 1. Okay, so block 1 is just x++, okay, with the semicolon, and then we'll define the condition C, which is just going to be, I don't know, let's say this is x is less than 3. Okay, so we just want to go through the loop 3 times. Okay, so with these already in place, then we can just say init over here without the semicolon, and then we now can say while C, and inside C we perform block 1 without the semicolon. Now if you want to leave the semicolon out of the macro definition and put it into the actual C code, that's fine too. Okay, there's no problem with that. Okay, so we can just put it here and put an open curly brace, put it here and curly brace. Okay, so that should work too. Now in the second one, which is the flattened version of a while loop, now we can reuse the macros. This is why the macros are useful, because in this case we have init, which is irrelevant to the translation of code, because that's just how we declare the local variable and also initialize it to 0. And then we have L1, which is the label to go back to, and then we have block 1, Oh, nope, I forgot about that. If not C first, okay? Now, if we are going to use negation on C, it is usually better to include a pair of parentheses. So this way, no matter what we do with the macro deficiency, it will still work. Okay, we can apply operators around C, and with the extra pair of parentheses around x is less than 3, we don't have to worry about the precedence of operators. So if not C, we want to go to label L2, which is the continuation label. And if condition C is true, which means not C is false, we are not going to label L2, and instead we have block 1 to perform. And then we have a unconditional go to back to a label L1, and then we define late L2 over here. And we just give it an empty block right after, because otherwise the compiler complains that I cannot have a label definition at the end of a block, which is a whole lot of nagging, okay? But in this program, that's how we want it to be defined. Okay, so this program is pretty much done. And then we have main. We define main over here. And because this time we don't have any parameters to worry about, we can just kind of call both of these one by one. But the way it is right now, block 1 doesn't print anything, so we'll go ahead and say printf percent x equals to %d line feed, and then specify x. So I'm just including a little bit of printing so that this program is easier to track just by running it without using the debugger. All right, so okay, so now we need to call while 1, and then we call while 2, and just to be more clear, okay, while 1 is gonna run like following, and then while 2 is gonna run like the following. All right, so just defining some additional stuff so that we can interpret the output, which portion is the result of running while 1 and which portion is the result of running while 2. So let's exit this and recompile the code. Oh, okay, I don't have any recompiling because we have never compiled this particular one. So warn all, include debug information, and make the output called while, and the source code is while.c, like so. And then we run while, and we can now see the behavior of both versions of the loop are identical. Okay, one just looks a little bit messier than the other one. So let me show you what I mean by that. So we can see that the translation was successful. They behave in exactly the same way, except this is more structured because of the use of the, guess what, curly braces. This one is flattened because we do not have the curly braces anymore, but it behaves exactly the same way as the first one. Okay, so this is the second chunk of today's recording, and I am going to upload it so that you guys have access to it whenever you want to.